Hi guys, in this video I am talking about multi-channel analyzer. So let us discuss about the basic components and its function. The multi-channel analyzer is comprised of the basic components illustrated in the figure given below. Its operation is based on the principle of converting an analog signal, that is the pulse amplitude, to an equivalent digital number. Once this conversion has been accomplished, the extensive technology available for the storage and the display of digital information can be brought to bear on the problem of recording pulse height spectra. As a result, the analog to digital converter is a key element in determining the performance characteristics of the analyzer. The output of the ADC is stored in a computer type memory which has a many addressable location as a maximum number of channels into which the recorded spectrum can be subdivided. The maximum content of any one memory location ranges up to 16.8 into 10 raised to 6 counts. The basic function of the MCA involves only the ADC and the memory. For the purposes of illustration, we imagine the memory to be arranged as a vertical stack of addressable locations ranging from the first address or channel number 1 at the bottom through the maximum location number at the top. Once a pulse has been processed by the ADC, the analyzer control circuits seeks out the memory location corresponding to digitalized amplitude stored in the address register, and the content of that location is incremented by one count. The net effect of this operation can be thought of as one in which the pulse to be analyzed passes through the ADC and is sorted into the memory location that corresponds most closely to its amplitude. This function is identical to that described earlier for the stacked single channel analysis. Neglecting that time, each input pulse increments an appropriate memory located by one count, and therefore the total accumulated number of counts over all memory is simply the total number of pulses presented to the analyzer during the measurement period. A plot of the content of each channel versus the channel number will be the same representation of the differential pulse height distribution of the input pulses for the stacked single channel analysis. A number of other functions are normally found in a MCA. In the figure, an input gate is usually provided to block pulses from reaching the ADC during the time it is busy digitalizing a previous pulse. The ADC provides a logic signal level that holds the input gate open during the time it is not occupied. Because the ADC can be relatively slow, high counting rates will result in situations in which input gate is closed for much of the time. Therefore, some fraction of the input pulses will be lost during this dead time, and any attempt to measure quantitatively the number of pulses presented to the analyzer must take into account those lost during the dead time. To help remedy this problem, most MCAs provide an internal clock whose output pulses are routed through the same input gate and are stored in a special memory location. The clock output is a train of regular pulses synchronized with an internal crystal oscillator. If the fraction of the time the analyzer is dead is not excessively high, then it can be argued that the fraction of clock pulses that is lost by being blocked by the input gate is the same as the fraction of the signal pulses blocked by the same input gate. Therefore, the number of clock pulses accumulated in channel 0 is a measure of the lifetime of the analyzer, or the time over which the input gate was held open. Absolute measurements can be therefore be based on a fixed value of lifetime, which eliminates the need for an explicit dead time correction to the data.